For centuries, we thought we pretty much understood the rhythm of our star. We saw it as this simple 11-year beat, all defined by sunspots appearing and disappearing. But what if that was just the loudest instrument in a massive orchestra? What if a brand new discovery has just uncovered a hidden symphony playing across the sun, completely changing what we thought we knew? Okay, so to really get why this new finding is such a huge deal, we've got to go back to the classic story, the one most of us have heard about how the sun works. Ever since 1844, our whole picture of the solar cycle has been built around this one thing, sunspots. We count them, we track them, and we watch them come and go over that 11-year cycle. It's the most obvious, most dramatic sign of the sun's magnetic chaos. Seemed pretty simple, right? Predictable even. But what if focusing on just those big, dramatic sunspots meant we were missing almost everything else that's actually going on with our star? What if the real story was hiding right there, in plain sight, the entire time? And that brings us to the rest of the sun, the huge areas that don't have sunspots. Scientists just call it the quiet sun. And for a long, long time, everyone just assumed it was, well, quiet, maybe a little boring. Turns out, that assumption was completely and totally wrong. Yeah, see, the quiet sun isn't empty, not at all. It's this fizzing, crackling landscape just packed with countless tiny magnetic fields. The researchers who wrote this paper described it as a salt and pepper pattern of north and south magnetic poles, all churning away constantly. And here is the first absolute bombshell from this new study. This chart right here compares the total magnetic energy, the flux, in those active sunspot regions versus these so-called quiet regions. And just look at that. For almost the entire solar cycle, the quiet parts of the sun hold more total magnetic energy than the loud, flashy sunspots that get all the attention. In fact, up to 85% of the sun's entire surface is covered by these quiet fields. Think about that. This isn't some small detail we overlooked. This is the main magnetic feature of our sun. We've basically been focusing on the 15% of the story while ignoring the giant elephant in the room. So if the quiet sun is so important, you'd think we'd have a pretty good idea of how it relates to the 11-year sunspot cycle, right? Well, for decades, it was just a massive puzzle. The data was a complete and utter mess, and it led scientists down all kinds of dead ends. And I mean, just look at the confusion. Depending on which study you picked up, these little magnetic fields either got stronger with sunspots, or they got weaker with sunspots, or they did nothing at all. It was this classic scientific mystery, and nobody could figure out why all the results were contradicting each other. The problem, it turns out, was the data itself. A lot of the older observations were patchy, or just not sharp enough to see what was really going on. To crack this puzzle, we needed to just stare at the sun, nonstop, with an incredibly powerful eye. And that's exactly what NASA's Solar Dynamics Observatory, the SDO, has been doing for 15 years straight. And with this absolute fire hose of perfect continuous data, the team finally made the breakthrough. The quiet sun isn't one thing. It's got a split personality. It's home to two totally different kinds of magnetic structures that behave in completely opposite ways. And this lays it out perfectly. On one side, you've got these stronger magnetic fields that are in phase. You can think of them as friends of the sunspot cycle. When sunspots increase, they increase too. But on the other side, you have these much weaker, but way more numerous structures that are antiphase. They're the foes of the cycle. When sunspots increase, they actually decrease. This is it. This is why the old data was so confusing. Scientists were unknowingly averaging together two signals that were completely canceling each other out. And here's the real kicker. Just look at this. When you actually count them, it's not even a contest. Those weaker, antiphase structures, the ones that do the opposite of the sunspots, make up over 95% of all the little magnetic features in the quiet sun. They are the vast, silent majority. So now that we have these new puzzle pieces, we can finally put it all together. We can tell the complete story of the solar cycle for the first time. Okay, so here's how it works. During solar maximum, when there are tons of sunspots, those big decaying active regions, like the one on the left, are constantly breaking apart and shedding their magnetic energy. They're like a source, feeding over 60% of the magnetic energy into that huge quiet sun network on the right. But what happens during solar minimum, when there are barely any sunspots left to be a source? Well, that connection gets cut. The energy coming from active regions drops to less than 10%.
And yet, the quiet sun is still buzzing with magnetism. This proves it has to have its own power source, something called a local dynamo. You can think of it like millions of tiny independent generators, totally dominated by those anti-phase fields, all creating magnetism on their own.
So this is the big takeaway. The sun's magnetic engine isn't a single system. It's a two-part system. There's a global one tied to the sunspots that runs the show during solar maximum, and there's a local one, totally independent of sunspots, that keeps the quiet sun humming along during solar minimum. It's this dynamic, two-engine system that we just never saw before. And that brings us right to the powerful conclusion from the scientists themselves. They basically say that to really understand the solar cycle, we can't just look at sunspots anymore. We have to look at the quiet regions that they influence and interact with. The quiet sun isn't just a passive bystander. It is an essential and sometimes the most important player in the sun's secret symphony.